All right, cool. Well, I really appreciate the opportunity to speak at the Stanford Robotics Seminar. It's really cool as a PhD student. I'm sure Samrita will agree to be able to share our research with folks here at Stanford and folks watching at home. So today I'm excited to share some of my research during my PhD, which proposes the idea that wearing a virtual reality headset while driving a car could potentially help us improve vehicle safety. And I'd like to start with a quick introduction. I want to show some of my colleagues who I've gotten to work with throughout my PhD. So I'm a student in the Dynamic Design Lab. It's a group in mechanical engineering led by Professor Chris Gerdes. And we do a lot of testing on real vehicles. This is one of our test vehicles here. And the lab focus is really on enhancing safety on the road by doing different research projects on vehicle dynamics and control. We've done a lot of work looking at vehicles at and beyond the friction limit. So we've done work autonomously racing and drifting vehicles. And my particular interest, as Mark had pointed out in the introduction, is on automotive human-machine interaction. So I'm really interested in designing driver assistance systems that work with and around human drivers. And one of the scenarios that's motivated my work is a situation that sometimes occurs when you're driving on a backcountry road where you may have to overtake another vehicle. So imagine you're driving in that blue vehicle and you sort of have to choose the moment to go from following to overtaking this vehicle. And this is a potentially dangerous situation, especially at higher speeds and with another vehicle coming in the oncoming lane. So I'd really like to think about how to design a driver assistance system to support drivers in such a scenario. And one promising paradigm that we've been looking at in our group is what's called shared control. So it's the idea of a system that can blend inputs with the driver. So rather than just taking over control and then handing it back to the driver later, it's something, a simple example of shared control would be like a lane center assist system that provides little nudges on your steering wheel to help you track the lane. But I'm interested in extending these systems to much more complex scenarios. And a question that has come up in thinking about how to design a system is how might we test novel shared control architectures in safety critical scenarios with other road users. And this has turned out to be sort of a challenging problem because in order to show that our system works well, we want to run lots of tests of it. And some of the challenges that arise when thinking about how to test shared control architectures are that we know that drivers rely on a lot of different sensory cues to control their vehicle. For example, the feeling of the motion of the vehicle that people sense with their vestibular system in their inner ears, as well as haptic feedback they get from the steering wheel and the pedals. We also would like to validate systems that we design across a variety of test conditions and ideally on a real vehicle. Well, doing testing on a real vehicle at a test track can be expensive and we're often limited by the space of the track. And it can also be dangerous to run experiments, obviously, with other road users. So the solution that I will suggest, as the title of my talk sort of proposes, is to immerse the driver of a real vehicle in a virtual driving scene. This is something known as vehicle in the loop. And I'm not the first person to think of this idea. In fact, this was first proposed all the way back in 2007 by some really talented engineers at Audi that built a system where you have a driver in a real car and they're wearing an augmented reality headset and they see virtual lane lines and virtual other vehicles in view. And there have been some examples of more recent vehicle-in-the-loop systems using virtual reality. So this is now where the driver has no view of the real world. And this has been used for various human factors studies and for driver assistance system testing, which is what my real interest is. And I'll note that so far, these other platforms have been limited by the dynamics of production test vehicles. What I mean by this is if you want to have a vehicle that handles differently, go from a Prius to a Tesla, or drive on a different surface, go from dry pavement to snow, you need to change the vehicle, or you need to go to somewhere that has this different surface. But we have a really nifty tool in our arsenal, which is our test vehicle, X1, that you've seen also on the first slide of this talk, that was built in our lab about 15 years ago now, and we still use it for testing today. And it is an all-electric, four-wheel steer-by-wire vehicle. And what this means is four-wheel steering means we can independently control all four of the wheels. So we can have the rear tires steer as well as the front tires. And this allows us to precisely modify the handling dynamics of the vehicle. I'll give a couple of examples of that. And it's a steer-by-wire system, meaning the hand wheel, the steering wheel, is not physically connected to the road wheels. So we can have a system that has the road wheels steering a little bit differently from the driver. And we also have a motor we can put on. We have a motor that's attached to the hand wheel that can give the driver custom haptic feedback to give them different steering feel. And so one of the early projects that I did in my PhD was building a vehicle-in-the-loop platform around X1. So here's a picture of me wearing a virtual reality headset. And as I'm driving around in the real world, I am looking at a first-person view inside a virtual vehicle whose motion corresponds to the motion of X1 as we can measure it with high-precision GPS sensors. So let's take a look at what this looks like in a video. So I'll put on my VR headset here. I'll note that my colleague Alessandra is just wearing normal safety goggles. She actually can see the road. And we're at a closed test facility here where we test. And I've overlaid a virtual oval track on this rectangular skid pad area. Maybe we can turn the video volume down a tiny bit. And you can see as I round the turn here, we have some cones in the virtual world that correspond with cones in the real world, sort of to demonstrate that even with the VR headset on, I can still navigate through this sort of scenario. So again, what we're seeing on the main screen here is what I'm seeing in the VR headset while I'm driving. So as I've discussed, because we have this flexible vehicle, X1, we can test in a lot of different configurations. So what we just saw was what I'd call a nominal dynamics configuration. This is sort of the current state of the art in vehicle-in-the-loop, where we don't modify the dynamics at all. I'm just driving the vehicle manually. But we can also test in a low-friction environment and match that up with a low-friction or a snowy scene in the virtual world. And this is obviously very useful because we don't get a lot of snow and rain out here in California where we do our testing. And even if we did, X1 has a lot of exposed wiring, so I'm not sure we'd want to get things wet on the car. And then another cool thing we can do is test in a scaled speed scenario. So I call this high-speed emulation. And the idea is we can scale up the speed of the virtual vehicle so we can run tests at, say, 60 miles per hour on a limited track area. And now I'll give a little bit more information how the low friction and the high speed configurations work. So low friction emulation is a concept that was introduced by a former lab member, Holly Russell, about 10 years ago. And it's an idea to get the vehicle to handle as if it's on a snowy or icy surface. And the way that it works is we take the driver's inputs and pass them through a reference dynamics model. So we simulate the motion of the vehicle as if it were on a snowy surface, say with a friction coefficient of 0.3. That's the friction coefficient between tires and snow or snow and ice. And then we can calculate what the yaw rate, R, that's the rotation of the vehicle, the longitudinal velocity, UX, and the lateral velocity, UY, would be in this snowy surface. And then we can track these three velocity states on X1 on a high-friction surface using the four-wheel steering capabilities of X1. In this case, the controller tends to make the rear wheels steer in the opposite direction of the front wheels, and it gives this sort of exaggerated yaw motion that simulates the feeling of fishtailing on snow and ice. And then something that I've done, and part of my work in my PhD, has been building on this and creating what I call high-speed emulation. And this is something that specifically takes advantage of having the VR headset in the vehicle. And the idea is to scale up the speed of X1 in the virtual world by a constant factor and practice a factor of 2 or 3. And then in this case, we're interested in tracking the lateral acceleration and yaw rate on the real vehicle so that the driver gets the sensation of motion that they would expect in their vestibular system while they're making lane changes at this higher speed. So what this looks like is if in the virtual world, the virtual vehicle is going at 60 miles per hour and the driver's taking, say, a somewhat aggressive turn at 0.5 Gs of acceleration, we can exactly track that acceleration and yaw rate, or get close to exactly tracking that, with a controller that, in this case, tends to steer the rear wheels in the same direction as the front wheels. So X1 has this kind of exaggerated crabbing motion that gives that feeling of lateral acceleration that one would expect at a much higher speed. And I'd like to show a little bit of data from one experiment to show sort of how the controller works. So the top plot here is the yaw rate, middle plot is the lateral acceleration, bottom plot are steering angles, delta. And in the top plot, we can see that the real yaw rate on the vehicle tracks the reference signal in orange within human perception thresholds. So we can look at various human factor studies that suggest as a conservative value, maybe 2 to 3 degrees per second is the sort of minimum threshold of yaw rates between which people can't discriminate the difference. We also see that the lateral acceleration on the real vehicle tracks the reference value and adds this sort of higher frequency content on top of it. And that's actually reflecting the vibrations of the real vehicle, which is something that helps further immerse the driver. And it also is something that moving platform driving simulators that maybe folks have seen before at car companies that kind of slide the driver around can sometimes struggle with these vibrations. But we get those for free in X1. And then at the bottom plot, it shows in the orange and yellow dashed lines how the steering angles tend to kind of track each other to both track the yaw rate and the lateral acceleration together. So as I mentioned up front, the real purpose of this is to develop shared control systems that can help drivers in difficult driving situations. So now I want to provide a little bit of detail on a shared control system that we've used and tested in these different settings. So what I'm going to present here is what's called a receding horizon shared control system. It's also known as model predictive control, where we can measure the vehicle's state at the current time step and then project out over the next 3 seconds with a series of discrete states where the vehicle may be, and basically solve for a trajectory over that 3-second horizon that optimizes for different parameters and use that to share control with the driver. So the idea here is we want the system, in this case, to try and track the driver's inputs on the steering, the throttle, and the brakes, but we allow the system to intervene as necessary using steer-by-wire and throttle and brake-by-wire on the vehicle to help keep the vehicle within road boundaries, to avoid other vehicles, in this case in the virtual world, and also to do this while respecting coupled lateral and longitudinal vehicle dynamics. And I'll note that this controller is based on work from one of my colleagues, John Talbot. And now I'd like to show a couple of experiments with this controller running in these different conditions, so a low friction experiment and a high speed experiment. So let's imagine we want to test how the controller performs in supporting a driver on a hairpin turn on an icy surface or a snowy surface. But we only have access to this dry pavement road. You can actually verify that it's sort of a sunny day by looking at how brown the grass is around the track. So this is at the same facility from the earlier video. Our lab goes to Thunderhill Raceway to test our vehicles, and this is turn 10 on the west track. And we can turn this into our snowy hairpin experiment by putting our test vehicle with this low friction emulation overlaid on the track. So now what you'll see in this video is the snowy virtual world that I'm seeing in virtual reality, as well as you can note that the car is emulating low friction dynamics. And also one thing I didn't explicitly talk about, but that is part of this experiment, is the steering feel on X1 has been modified to reflect the sort of lower forces that one would expect to feel while driving on snow. And then you'll see these dots visualized for the driver, the MPC horizon, the horizon of the controller. And then we can also take a look at how the system intervenes to keep the driver safe. So in blue is the driver's steering angle, and in red is actually the road wheel angles that sometimes differ in order to keep the driver on the road. So we'll start the experiment here again. I'll emphasize it's a dry, sunny day, but to me, driving this car, I feel like I'm in, Chicago in the middle of winter. And we can evaluate the performance of this shared control system. So we can see that it kind of tracks my steering at first, and then I'll try to steer off the road to the left here. The system steers me back to the right. Going into the turn, the car is actually slowing down a little bit to keep me from sliding out. since this is an emulated low friction environment. And then again, I'll try to steer off the road. The system will kind of help catch me here. And one really cool thing about this work is that this was sort of part of the development process for my colleague John's shared control work. And we then took this controller. He was able to then take the insights from testing this controller in this emulated low friction surface over to a winter testing facility that we test at in Sweden, and actually run this controller on real snow and ice. So this sort of shows that these sorts of techniques can provide a nice intermediate test bench between simulation and the very expensive trip to Sweden that requires flights and testing on an actual snowy surface. So we'll now return to the motivating scenario that I was interested in for the second experiment, which is a highway overtaking scenario. And here we'll see a shared control system that helps the driver overtake the lead vehicle while getting back onto the road before the oncoming vehicle gets to them. And I'll emphasize that the skid pad, which is just a big rectangular parking lot that we test at Thunderhill, only gives us maybe 200 meters, in reality like 180 meters with safety bounds to test on. But if we scale the speed up of the virtual vehicle and kind of overlay that on the track, we can run an experiment at much higher speeds and safely run this test on the track while the driver gets all of the vestibular, haptic, visual feedback that they would expect at this higher speed. So we'll see a similar video here. You'll see the MPC horizon. You'll see the system sort of intervening. And I'll note that the real vehicle, X1 in the upper right corner, is only driving at 1/3 the speed of the virtual vehicle. So I'll start the test here. And the scaled speed technique quickly gets me up to a speed where we can turn on the driver assistance system. And then the system sort of finds a gap between the two vehicles. It's actually giving me a little throttle there. And it steers me to the right to avoid that oncoming vehicle. And then I sort of try to steer off the road, and it helps keep me on the road again, the virtual road, where you can see we're well within the confines of the real world here. I'll play this video one more time so we can take another look since it's kind of quick. And I'll emphasize that this is the type of experiment that would be way too dangerous to run with other real vehicles and or at these speeds. But with our vehicle-in-the-loop platform and scaling the speed up, we can give the driver a somewhat frightening experience, but still have them drive safely and see how it feels to drive with some sort of novel shared control technology. And what we saw here is an example of a system that sort of assumes that the driver wants to shoot the gap. What I don't really have time to talk about today, but has been sort of the second part of my PhD work, has been building on this to develop controllers that can help drivers sort of make decisions between following the lead vehicle versus overtaking and make lane changes on the highway. But the point here is really to demonstrate that we can test these sorts of systems safely and in a very immersive and evocative driving platform. So a few takeaways from today. Vehicle in the loop, which is wearing a VR headset while driving, can provide a balance of realism and practicality for shared control testing. And specifically designing our vehicle in the loop platform around a 4-wheel steer-by-wire vehicle like X1 can enable us to test in various conditions. And in my mind, we now have the tools to develop assistance systems that can help drivers navigate the road more safely, because that's really the ultimate goal of this, to use this as a tool to develop better driver assistance systems. So thank you, and I'm now ready to take your questions. Yeah.
What's the maximum rear steering angle that you guys achieve on this vehicle?
Can go up to 33 degrees. Yeah, it helps a lot. The front steering angle is constrained to 18 degrees. So when we're trying to load the car into the truck or drive around the track, we almost always turn on the 4-wheel steering so we can actually maneuver it around. But that's thanks to the work of several colleagues that predated me that built some really nice, you can't quite see it on the picture here, but really nice rear suspension and steering geometry to get these really big steering angles. Yeah.
So like when you are emulating the low friction scenario, because like when we are actually accelerating, the acceleration of the vehicle will be lesser in the snow because of lower friction. Like in the real world, it would be higher. So how are you trying to emulate that particular? Like the vehicle, we just matching the speed of the test vehicle speed and the emulated vehicle speed. They would just match, or the longitudinal acceleration would also match.
Yeah, that's a good point. I can actually go back to that slide. I think implicit in this slide here, where I discuss low friction emulation, is the idea that if we can track these three velocity states, so basically the three velocities that define the planar motion of the vehicle, then this also enables us to track the accelerations, because the lateral and longitudinal acceleration of using a planar vehicle dynamics model is just the derivative of UI or UX plus another term that accounts for the rotational component of acceleration. That's R times either UI or UX. And basically, if we're tracking these three velocities, then we would expect to get the same accelerations on the real vehicle that one would expect while driving on snow. So, for example, if I just punch it, if I step on the throttle and try to go as fast as I can, I will only get the longitudinal acceleration that I would get on the low friction surface on the real car. Does that make sense? Any other questions? Yeah.
I'm curious, when you think about shared autonomy, to what extent can it tell you you're not allowed to do that? Like I saw in that video, you were like trying to go out of the lane and it kept you there. Do you think in the future there should be things that like fully don't let you take actions that you want to take as a driver?
Yeah, this is a big question. This is like one of the big things that I've been thinking about, and I don't really have a complete answer to it. I think one thing that we found with this controller that we saw in the video is it can feel a little bit, you feel like you're kind of taken out of the loop as a driver when you go to steer off the road, and then suddenly without any feedback or anything at all, the car just kind of bumps you back. It can also feel kind of cool that the car is catching you in this way and is helping keep you safe. I think haptic feedback on the steering wheel, which is something I worked on in later versions of the controller, is really important. And then another big aspect of this is if we start thinking about this as not just shared control, but shared decision-making and control and deciding between different maneuvers, we have to think about who's really making the decision of what maneuver to do. And one of the tools that I've used in my research is actually a design metaphor. And I think about designing a driver assistance system in the context of partner dancing, actually. That's something that I'll talk about in my thesis defense. And the idea is we imagine the driver as the lead, and they're guiding the system as the follow through sequences of maneuvers. Then we sort of have a bit of an asymmetry between the driver and the system, which can sort of help disambiguate who is in charge of what aspects of decision-making and control. But this is still like a big open question, and a lot of HMI researchers are, trying to come up with the best answers. Yeah?
Maybe this would be more appropriate for training. You could come up with a modulation of this that helps people be better drivers.
Yeah.
And then you wouldn't have to answer all these thorny questions. And also, right, I mean, I think you can only take headsets so long, right? That's been my experience.
Oh, as in you get motion sick?
Well,
leaving it on
there's
for
just
too
lots
long?
of things, right? I mean, it seems if you had something where you could actually do a heads-up display in a car, then people would be happy with whatever. But
Yeah. Well, I would not suggest at all that we have real drivers wear VR headsets on the real road. And I also wouldn't really suggest that we have passengers wear VR headsets either, because I just think too much time in VR in general is bad in many ways. And the heads-up display can definitely give certain bits of information to the driver, like the trajectory and the deviation that the system is planning. Specifically for this work, the VR headset is really nice because we can totally block out the real world, so the driver feels like they're in this sort of alternate reality, and they get the motion cues that match that, which kind of helps with simulator sickness. But I agree with a lot of the points.
And might this also not have more application early on in training race drivers?
Yeah.
People that are in really extreme situations.
Yeah, definitely. I think training is a big focus area for this. And I know, for example, to get a driver's license or to be able to drive test vehicles in a lot of European countries, because there's a lot of snow in a lot of northern and central Europe, people have to go to actual ice facilities and practice, keeping the car from spinning out on a snowy surface. Some of my collaborators in Europe have described some really fun but important training sessions they've done, and I think this can be a nice tool for that too. So I totally agree.
We don't have any more questions.
Yeah.
Let's